All right.
Hey, would you care to do the honors?
Recording has started. Let's. All right. Plan for today looks like this. First, I want to just review the calendar a little bit, make sure we know what's going on, what's coming up, when things are going on, blah, blah, blah. Then we're going to get to our next topic, dealing with energy and mechanical energy, and that's conservation of mechanical energy. First, calendar. Yesterday, actually Wednesday for you guys, you took your data for the next lab that deals, or the lab that deals with this section of the energy units. Then at the end of the period, we went over the details for your formal lab report. There is a link on Wednesday that shows you the things that you need to do, things you need to include, things you don't need to include. So make sure you take a look at that while you're preparing your lab report. Okay? The stuff we're going to do today, conservation of mechanical energy, definitely applies to your lab report. So after today, you should have the information that you need in order to write your testable question, do some of your analysis, do some of your background information, that kind of stuff. Okay. Next week, first I will update this on the calendar if I haven't yet. Test corrections are going to be due on Monday. Also on Monday, you're going to have a take-home quiz. I know it says that I was going to give it to you take-home on 420, but I don't have it ready for you yet, so I'll give it to you on Monday, take-home for Tuesday. Okay, over the first part of this unit. Then we'll get into temperature, heat, thermal energy. We'll continue on with that on Tuesday. Wednesday's lab deals with temperature and heat, thermal energy. Friday we'll do energy transfer. Wrap it up on Monday. Review Tuesday. Test Wednesday. Not of next week, but the following week. Questions there?
What is due at Monday?
Oh, the lab from Wednesday. So we'll get to that. All right. Oh, lab report due next Friday. Good. All right. We established that.
Oh yeah.
Seriously.
I thought it was over that.
We have past Wednesday. All right. The next topic that we cover in dealing with energy deals with this idea of conservative forces and non-conservative forces and conservation of energy. When you look at the literature review, there were like 6 terms that I wanted you to include. You know 4 of them already, but there were 2 that you don't know yet, and those were conservative force and non-conservative force. We'll talk about those today. This discussion starts off with conserved quantity. When something we say is conserved, what does that mean? It's saved, or if it remains what? Let's not go. Remains constant. Okay, remains the same. That if we go to measure that conserved quantity, what would we see about its amount at the beginning of the situation versus the end of the situation? It should be the same. We discussed a conserved quantity earlier this year. What was that conserved quantity that we studied in chemistry? Mass is a conserved quantity, right? You did a lab, remember, where we put the baking soda and vinegar into things, and a lot of you put the balloon on top of the bottle to try and capture the gas, right? Not that it always has to look the same, but if we talk about any conserved quantity, whatever we start with has to be there at the end. So we know that mass is a conserved quantity, but energy is also a conserved quantity. That if we look at the total amount of energy in a closed system, it will remain constant. So if we look at the total amount of energy in a closed system, it will remain constant. So, 2 things. First, what's a closed system? We talk about a closed system. What does that mean? Say again? Nothing can interrupt, right? Nothing interrupts. No interaction with the surroundings. Okay? If we talk about total energy, what does that mean?
All kinds.
All kinds of energy, right? we talk about not just the mechanical energy that we've been discussing for the past couple of days, but also heat and electromagnetic, nuclear, and all those different kinds we talked about on Monday. That the total amount of energy is always conserved. Okay? If you want to take a look at it and think about it from a big picture standpoint, okay, the ultimate closed system is the universe itself. Does anything ever get in or out of the universe? Because the universe is everything, so nothing can get in or out, okay, like we ask. But anyway, so that means that the total amount of energy in the universe today is equal to what? The amount of energy there was at the very, very beginning. However, you believe that universe started, right? You know, believe that there was a big explosion, whatever, okay? I'm not telling you what to believe, I'm just saying however the universe started, right? Whatever energy was there at the beginning has to be there at the end. Okay? Get it? Alright. Let's next talk about mechanical energy, which hopefully is a review. So we said mechanical energy concerns us with what about objects? Kinetic and potential are what makes up mechanical energy, but we said mechanical energy, motion and position or location, right? So mechanical energy deals with motion and location. And we said that the specific types of energy that show us that motion and location are kinetic and potential. But we said there were two kinds of potential, right? Gravitational potential and elastic potential. And that the sum of those three, the total amount of those three all together, make up the mechanical energy of a system. Why are we so concerned about mechanical energy? Because that's what we deal with on a pretty everyday basis, right? It's energy of big things, like you and me and basketballs and trains and whatever, okay? And it deals with how they move and their locations. And those are the things we deal with on a pretty everyday basis, okay? Good with mechanical energy? Hopefully that's a review. All right, go ahead, Ella.
So if you calculate the mechanical energy, is that not the total energy of the
Correct.
thing?
The mechanical energy of the system is not the total energy of the system, okay? For example, right? If I go here, right, and I do this, okay, what have I done to my mechanical energy? I've increased it because where am I now? I'm up higher. I have more potential gravitational than I did before, right? If I'm moving now, right, now I have potential gravitational and kinetic, okay? But if we look at all those other types of energy, right, every cell in my body is made up of tons and tons and tons of atoms. All of those atoms have a nucleus. That nucleus, for me, is stable. But if we could somehow make that nucleus fall apart, nuclear energy, right? Also, all of those atoms and molecules that make up my body, they're vibrating, right? And now they're vibrating even faster because I'm moving around and that creates heat, blah, 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 right? So when we look at all of those things together, then we're talking about total energy. Mechanical energy is just one form of energy, okay? But, that's the kind that we deal with on a kind of regular basis, right? All right. Next. Maybe. Conservative forces. Conservative forces consist of two things. There are two kinds of conservative forces. Gravity, and then elasticy, springy things, like rubber bands and slinkies and stuff like that. Okay? What makes conservative forces special? Conservative forces do not change the amount of mechanical energy in a system. All they do is convert one form of energy into something else. One form of mechanical energy into something else. So gravity and elastic forces are conservative forces, and what makes them special is that they do not change the amount of mechanical energy in a system. For example, baseball. I hold it up here. What would we say about its kinds of energy that it has? Let's go mechanical. What kind of mechanical energy does it have? Potential gravitational, right, because of where it's located. Most likely we're going to call the ground like our reference point, our 0 point. If I let this ball go, right? What? Good. If I let the ball go, what's going to start happening to it? It's going to fall. But as it falls, what happens to it? It gets faster, right? So Alex, by the fact that it's falling, what's happening to its gravitational potential energy? It's getting smaller. But as it's falling, right, what's happening? You said what's happening to its speed. So what's happening to its kinetic energy? It's also increasing, right? And the thing that makes gravity special, or gravity a conservative force, is as this thing falls, its potential energy is decreasing, but its kinetic energy is increasing. By how much? The same amount. It's like a seesaw, right? At the beginning, it's all potential and no kinetic. But as it falls, potential goes down, kinetic goes up. Right before it hits the ground, that very instant before it hits the ground, what could we say about its energy at that point?
Maximum.
It's maximum what?
Kinetic.
It's maximum kinetic, but how much potential? None. So, Nick, if we talk about it started with this much potential energy, how much kinetic energy will it have right before it hits the ground?
Probably the same as it did at the very
The same amount of potential as it had at the beginning. Okay? And that's what makes gravity special. Okay? If I attach this ball to like a spring, right, and I let it go, okay, as the spring stretches out, okay, its elastic potential energy is increasing because I'm stretching. But what happens to the ball as that spring is stretching out? It's going down, but also what's happening to its motion, right? Slowing down and stopping, right? So its kinetic is decreasing, but elastic is increasing. Could be gravitational as well. You know, I suppose if we did it sideways, that would make it a little easier, right? But if this is attached to a spring, right, I throw it, I give it some energy. As it's moving, the spring stretches out, right? Eventually it stops. I have a lot of elastic potential energy, but no kinetic energy, right? Then as it starts coming back, what does that spring do to the ball as it's coming back? Makes it go faster. So kinetic energy is increasing as potential gravity elastic is decreasing. Weird, go ahead. Yes, gravity and elastic forces are only the only conservative forces because they're the only one that cause the transfer of that energy, but not changing the total amount. Okay? Another example. Let's say now I take the ball and instead of dropping it, I throw it upward. First, do I do work on the ball at the beginning of the situation? Yes. Okay? I've applied a force, the ball moves because of my force. How much kinetic energy did it have before I applied my force? None, but now it has some. So I've changed its energy. But as soon as it leaves my hand, what starts happening to it? It starts, well, let's talk physically what happens to its motion. It slows down, slows down, slows down, slows down, slows down until it does what up at the top? Stops, right? And it's changing direction. Then it speeds up, speeds up, speeds up. Chris, what's happening to its kinetic energy on the way up? Decreasing. But what's happening to its gravitational potential energy? Increasing. When it reaches the top, how much kinetic energy does it have? None, because it's not moving. But how much potential energy would it have? A lot, or more specifically, the same that it had when I threw it. Okay? Parker, go ahead.
If you throw it up from like where your hand is, but let it hit the ground,
Okay?
what's the difference of the kinetic energy of your hand?
Okay. Let's talk about that. That, Parker, it would have the same amount of potential energy at the top as it had kinetic energy when I threw it if I called my hand like the starting point, right? Okay. But if I call the ground the starting point or the reference point, when I throw it, does it only have kinetic energy?
No.
It also has some potential energy because it starts off the ground. So really here, it has potential and kinetic. Here, kinetic is decreasing, but potential is increasing even more, right? So let's say, for sake of argument, okay, draw a picture of this. Come on. Of course, I don't have the right thing up to draw a picture of this, but okay. Stand by. We need some like elevator music.
Why don't you ever rock the board?
One, it's kind of dirty. Like it doesn't like show up right, it doesn't erase right. And two, I can draw here and I can save what I draw. So, you know. Is that good enough or?
Oh.
Yeah, it's good.
You want to say
What?
Because it's such a bad hand, I'll make sure I draw a good ball. So, all right. Yeah, definitely recording.
Four fingers.
One that big one that's joined.
Yeah, better.
No.
She said, "That's a little line
The big
goes
one.
straight down."
Don't make sense.
Oh, he's got 6 fingers.
All
All right. Anyway, so Parker, we just kind of talked about this, okay? If I say this is going to be my height equals 0, okay? Right when the ball leaves my hand, does it have any gravitational potential energy?
No.
Because I'm at height 0, right? If I have to go mgh or mgy, whatever we want to call it, right? I'm putting 0 into that formula. It has no potential energy. But what is it doing right when it leaves my hand? It's moving. Ooh, that's make it stop. No, wrong one. Come on. Okay. But it's moving at that point, so it has a lot of kinetic energy, right? But very, very little gravitational potential energy. As a matter of fact, no, it's because I just threw it, Allison, right? Let me, yeah, right when it leaves my hand. I'll add some whoosh lines to indicate that it's. So, here, technically, does it have any gravitational potential energy at this point? No. Okay. As it goes up, right? What do we know is happening to it? Slowing down, but it's getting higher. So at the top up here, when it stops, does it have any kinetic energy? No, but it has a lot of gravitational potential energy. Okay? Now, Parker, you said, what if we do this and make height equals 0 down on the ground, right? Okay? So, let's bring the ball back here, right when it leaves my hand, okay? And let's say I throw it with an amount of speed that gives it 10 joules of kinetic energy at that point, okay? But because it's off the ground, it also has some gravitational potential, let's say 10 joules, okay? As I go from here, where I threw it, to here, where it stops, the kinetic energy still goes down from 10 to 0. But what is going to happen to the gravitational potential energy here? It's going to go from 10 to what? To 20, okay? Okay. Now, Parker, here I think is what you were going to kind of ask about a little bit, okay? Let me clone. Okay. On the way back down, right? it starts with 20 joules of potential and 0 joules of kinetic. But now, as it gets to this point, except now we're going this way, right? When it gets back to this height, where I threw it from, how much kinetic energy is it going to have now? It's going to have 10 joules of kinetic energy. And because of the height it's at, it'll have 10 joules of potential. But now, Parker, once it passes the point where I threw it, what still continues to happen to the ball? It's still getting faster, right? So now, right, longer whoosh lines, right? If I'm halfway now between where I threw it and the ground, how much potential will I have? If I'm halfway between where I threw it and the ground, right? But then, what must have happened to my kinetic? And then, right before it gets to the ground, right, it's going even faster now. How much kinetic energy will it have at that point? 20, but 0 potential. So, Parker, in that case, I started with some potential gravitational and kinetic, and eventually turned it all into kinetic. But the important point being here, if gravity is the only thing acting on this, what do all of these sets add up to? They all add up to 20. Because gravity doesn't change the amount of mechanical energy, it just changes the form of potential or mechanical energy. Go ahead.
What if it hits the ground? What will happen to the
Now.
gravitation?
Good answer, or good question. Okay? So, good transition. This only applies for conservative forces. And we said conservative forces consist of two things, right? What are the two conservative forces? Gravity and elastic. Is the ground a gravity force? Is it an elasticy, springy force? It kind of depends maybe on what the ground's made out of, but let's say no. So now, when it hits the ground, is there a force applied? Yes, but is it a conservative force? It is not. So that leads us to non-conservative forces. Good transition. We did skip a couple, yeah, we skipped to the back side. So, let's do non-conservative force. Non-conservative force is anything besides gravity and a springy force. And more importantly, mechanical energy is not conserved. Okay? This equation probably looks kind of funny. Okay? But, if you think about it, it's conceptually what we talked about on Monday or Tuesday when we talked about work. The amount of work that you do is equal to what? What does the delta mean? Change in mechanical energy. Okay? So Alex, if we go back to our picture, okay, right before it hits the ground, it has 20 joules of kinetic energy and essentially 0 potential energy because it's right at the ground. Okay? But what do we know the ground does to this ball?
It's applied force off on the ground.
Let's say that it just like plunks. Like let's say the ground is soft, it just goes, right?
And then it just stops.
So it just stops. How much kinetic energy will it have then? 0. How much potential energy does it have? 0 joules. So how much work must the ground have done to that object? 20 joules. Technically, Caroline, it would be negative 20 joules because I took 20 joules of energy away from that ball. Does that make sense? Okay. So the amount of work I do is equal to the amount of change in energy. My hand. Is my hand a conservative force? It is not. So if I throw the ball, does its mechanical energy stay the same? It does not. Once it leaves my hand, Miriam, it does. But while I'm actually throwing it, what's happening to the kinetic energy of the ball? It's increasing, right? Because right now, how fast is it going? 0. But after I throw it, it's going fast. It's got kinetic energy. Didn't have kinetic energy before, now it does. Where did it get it from? Got it from me. I did work on it. My hand is a non-conservative force. How much work did I do? Well, how much kinetic energy did it end up with? Did it end up with 10 joules of kinetic energy? If it did, I did 10 joules of work. We refer to that idea as the work-energy theorem. How much work you do equals the change in energy. Okay? Are we okay with that? All right. For now, that's fine. Okay? Let's talk about this pendulum. So I take this pendulum, pull it back, right? When I pull it back, let's talk about this pendulum here. Okay? So I take it, pull it back, okay? Have I done work on it first of all? Yeah. Is my hand a conservative force?
No.
It is not. So I gave it energy. What kind of energy did I give it specifically? Gravitational potential. Once I let it go, what starts happening to it? Gravitational potential turns into kinetic, right? Then kinetic turns into gravitational potential. What's causing that to happen? Gravity. What do we say about gravity? Gravity is a conservative force. So, hint, theoretically, how much kinetic energy should it have at the bottom of its first swing? The same as the potential energy that it started with. Hint. Okay. So, if I let it go, I've done work to give it potential energy, but then I let it go, and gravity converts that potential energy into kinetic energy.
It's about to fall.
These are not sturdy. It's halfway off this.
I'm nervous.
So, now,
So wait, I have how, like, what would, like, in that case, the potential energy be when you're holding it? Would it be the strength of gravity, or?
it's MGH. Yes. Potential energy is how high off the ground it is, basically. Okay? But here, let's do this, okay? At this point, right? If I go...
I left something here.
So here, if I go potential energy at the beginning, no kinetic energy, right? If I let it go, kinetic energy increases, potential energy decreases. Once it swings past the middle, right, what starts happening? Kinetic energy again. Kinetic energy decreases, potential energy increases, okay? However, that picture. So, well, let's talk about
Does
that.
it ever?
First, does it ever stop? You ever watched the pendulum before? Yeah, it stops, okay? That means, can gravity be the only force acting on it?
No.
Because if it was, it would just keep going, and it would keep going exactly as high as it did before, exactly as high as it did before, exactly as high as it did before each time, okay? Anybody brave enough to do a quick demonstration for me? It involves a little danger.
Oh.
Okay.
My middle name is Danger.
Wow.
Wait, let me.
My other one.
All right. So, Parker, seeing as how you brought up this, got us into this discussion, let's go
What
ahead.
about the pendulum at the Great Lakes sites?
Okay.
That would, like, never stop.
It does stop. All right. So here's what Parker's gonna do. Okay, Parker. You're gonna go in the space there between the wall and the pendulum. Okay. Grab the pendulum with your hand.
Don't do it.
All right. Now, what I want you to do, okay? First, I want you to lean your head back against the wall. Okay. Get so that your face is like right in front of the. Yeah. Now crouch down. Okay. And hold the pendulum right to your nose or your chin. One of the two.
Oh my
Okay.
god.
Okay. Now, on the count of 3. Okay. I'm going to tell Parker to let the pendulum go. Not to push it, just to let it go.
Can I come back and
Miriam, question. What was your question? I heard you ask it.
Oh, is it gonna end? Or stop?
No. You just asked some. You just asked.
Oh, it's gonna hit his nose.
Is it going to hit his nose? Okay. Well,
Maybe.
let's talk about that. Okay. So, as we just discussed, is gravity the only force acting on this pendulum?
No.
It is not. That means all of the potential energy that he has right now, does it get converted back into potential energy when it comes back to where his nose is? Not all of it. If not all of it gets converted, will it hit him in the nose? It won't. Don't push it, just let it go. Keep your head against the wall. Yeah, it's really scary. The first time I did it, the teacher, the guy who I was doing my teaching with, he had like a bowling ball. And he's like, "Don't move." I'm like, "Oh." It took me like 3 times before I could move, but I eventually did. Anyway, we actually didn't finish up the notes. There's some reading assignment and some questions from the book. Okay, great. So you got somewhere to be, or? Okay.